So our next speaker is Ilya Sutskever. He's going to present a paper titled Sequence-to-Sequence Learning with Neural Networks. And his co-authors are Oriol Viñales and Kwok Lee from Google.
All right, thank you very much for the patience. This is work, so my name is Ilya Sutskever, and this is work that I've done with my excellent co-authors, Oriol Viñales and Kwok Lee. I suppose I could start with a joke of how many PhDs does it take to set up a projector. Okay, so the foundation of this work is the deep neural network. And deep neural networks have two properties that make them very desirable and attractive. So the first property of the deep neural networks is that they are powerful, which means that what it means is that they can perform an astonishingly wide range of computations. And there is a very good chance that they can compute the function that we care about. The second property of the deep neural network is that they are trainable. The fact that they are both powerful and trainable means that when we have a difficult problem, we can find the best possible neural network that solves a problem, and we'll get good results. One important point is that it is absolutely essential to use a powerful model. If the model that we use is not powerful, then it really doesn't matter how much data we have and how good a learning algorithm is. So for example, if you have a linear model or linear SVM or a small neural network, and it's basically impossible to get good results on really difficult problems. Small convolutional networks are the same because they have a small number of neurons and they cannot compute the right kind of functions that we want. The good thing about deep neural networks is that we can be reasonably confident that there exists a good setting of the parameters which achieves high performance, especially on perception tasks. And this is something which I call the deep learning hypothesis, although it's been known to connectionists back in the 70s. So the argument goes like this. Human being can solve a lot of very interesting problems in a fraction of a second, especially perception, vision, and speech. And yet our neurons are very slow, which means that it is possible to solve a very complicated perception problem using 10 massively parallel steps. So therefore, we can conclude that anything a human can do in a fraction of a second, a big 10-layer neural network can do as well. So this gives us confidence that if you have a hard problem, we just need to take a big deep neural network and we'll solve it if you have a lot of data as well. And very conveniently, it is possible to train these models with stochastic gradient descent. Now, despite their great power, deep neural networks cannot learn to map sequences to sequences. They can only map vectors to vectors. So for example, in visual recognition, it's pretty clear you got an image as a vector and you got a little category as an output. Or in speech recognition, neural networks are typically used to map a little chunk of speech into a little category that tells us what kind of phoneme it is. Mapping sequences to sequences is not something that neural networks can do, or at least could not do at the time when we were doing this work. And there are many applications to it which are very interesting. For example, machine translation, speech recognition, the recent image caption generation, question answering, summarization. All these problems can be expressed as you take a sequence which is an input and you produce an output. So our goal in this work is to solve the general sequence-to-sequence problem. We take an extremely simple approach, which I'll describe soon, and we achieve pretty good results on machine translation. So in this paper, our performance is close to the winning entry of the WMT14 English to French task, which is a real large-scale machine translation problem. And then we surpass this result in future work. So, but the real implication, the real take-home message from this is not that we can do machine translation, but is that we can do any sequence-to-sequence problem. Because machine translation is already pretty good. If you use Google Translate, you get good translations, and yet the system could match it, and it doesn't really assume anything about translation. If you have any other sequence-to-sequence problem you wish to solve, you can just plug it in without any thinking and get reasonable results, even good results. So what's the problem with deep neural networks? How is it that deep neural networks cannot solve the sequence-to-sequence problem? So the answer lies in the fact that different neurons have different connections. So for example, you can see that, for example, this neuron has its own set of connections, and the neuron that's next to it has a different set of connections. And what it means is that the neural network doesn't have a good way of generalizing across temporal patterns. If you see a pattern in time in one time step, then you see it in a different time step, it looks totally different. So you might say, okay, well, what about the recurrent neural network? The recurrent neural network deals with sequences. Can't you solve your sequence-to-sequence problem with the recurrent neural network? So here is a recurrent neural network in this figure. And a recurrent neural network is basically a regular, conventional neural network where you use the same connections at each time step. So what it means is that you can take a sequence of inputs and map it into a sequence of hidden units and get a sequence of outputs. So in a sense, you also map a sequence to a sequence with the recurrent neural network. And yet, I claim that it's not adequate for our needs. Why not? What's wrong with them? The main problem with recurrent neural networks is that there is a one-to-one correspondence between the inputs and the outputs. Oops. So as you can see, for each input, there is an output. You may have a sequence of inputs, and you produce a sequence of outputs, but both sequences are going to be of the same length, and they'll have the same alignment. Another problem with the recurrent neural network is that they are somewhat difficult to learn because they have the vanishing gradient problem and the exploding gradient problem, which were discovered by Hochreiter and then a little later by Bengio et al. And basically, luckily, the state of neural networks research has advanced, and now we can address both problems, both the exploding gradient problem and the vanishing gradient problem, and I will quickly present to you the way we solve them. So the exploding gradient problem means basically that sometimes your recurrent neural network exhibits very large sensitivity to perturbations. So your gradient is very large. So you do a very simple approach. You just say, hey, if the gradient is very large, you shrink it, like that. When it comes to the vanishing gradient problem, we use the long short-term memory, the LSTM. So the LSTM is a certain RNN architecture, which is different from the regular RNN architecture in such a way that the gradients basically don't want to vanish. The model is not different from the RNN. It is the same model. It can compute the same functions, but it is set up in a different way so that the gradients simply don't want to vanish at all. And the way it works is very simple. If you think about an RNN, what the RNN does is that it computes a totally new hidden state at each time step. So if you go back to the figure, you will see that you get a totally new hidden state. You combine the hidden state with the weights and you pass it through the nonlinearity, which gives you a new hidden state. And with the LSTM, what we do, instead of computing a new hidden state, we compute a delta to the hidden state which we add to it. So it looks like a minor difference. In the LSTM, you compute a delta which you add to the hidden state. But the implication is pretty significant, because at the end of the sequence, the final hidden state is going to be a sum of many little deltas. So even if you added a little delta to the hidden state of the LSTM at the beginning of your sequence, because the sum distributes its gradients evenly, every time step gets a gradient. The gradients do not vanish because of the sum. Now, the LSTM is still sensitive to the order of this input. You can say, well, it's a sum, so how does it know about the order? And the reason it knows about the order is because the LSTM decides what to add based on the sequence. So it's smart about what to add, but it's still a sum, so the gradients get distributed back evenly. Now, the LSTM looks like this, which is a pretty intimidating picture, which is why it hasn't become, even though it's been invented almost 20 years ago, it hasn't become really popular until recently. But nonetheless, once you implement the LSTM, you get your gradients you get your gradient check to pass, and then you know that that's it. You don't have to think about it anymore. It just works. It wants to work, and this is a very good property. Now we are ready to understand the main idea behind this work, which is extremely simple. The main idea looks like this. We use an LSTM, we feed it the input sequence, and then we ask it to predict the output sequence. And that's it. So there you go. This is the main technical contribution of this work. We use minimum innovation for maximum results. You see, So in this figure, you get a sequence of inputs, and you just feed it to the hidden state of the LSTM, and then you feed it a special symbol which says, hey, the sequence has ended. So now and now you just say, okay, now please predict the output sequence. It's really extremely simple. there isn't, from the modeling perspective, there isn't a whole lot going on here. But now let's try to understand what it really means. So the way it works from an objective function point of view is that we define a distribution of our output sequences given the input sequences, and we maximize the log probability of the correct answer using stochastic gradient descent. Now, you may notice that there is this bottleneck, which is the hidden state. You've got this long input sequence, which is mapped into a vector, and then you need to produce the target sequence. And that seems like, it may seem like this is a lot to ask from a hidden state to remember so much. So the way we address it is by using a large hidden state. We make sure that our model looks kind of like this. We use a deep LSTM. That's the minor departure from the previous picture. But again, the model is extremely uniform. We use this big, deep LSTM, so the hidden state over here is large. So it has a lot of capacity to remember whatever input you want. So that's it. This is the model. And then we just train it. And because deep neural networks are so powerful, it figures out how to solve the problem. Now, there is important, relevant, related work that I need to mention. So the first publication that discussed these kinds of models was by Niall Kalbrenner and Phil Blunsom, which used almost the same model, but they used a convolutional neural network for the encoder and then a recurrent neural network for the decoder. And then later, Kenyon and Cho et al. Have used an almost the same model. This work is simultaneous to us, with the difference that it was primarily used for rescoring a statistical machine translation system to rescore the proposal of such a system. And finally, the other relevant work is by Dimitri Bandau, Kenyon Cho, and Yosha Benjo, which used an attention mechanism for the same problem so that they don't need to use a large hidden state. And this is very interesting work. It's a very interesting model. So the difference, the main emphasis of our work is simply to show that this simple, uniform, uncreative model can achieve good results if the model is large. And so our main motivation here was to really try hard to produce the translations directly from the model. And the way you should think about it is that this work is a proof the naive approach just works. So I'll describe the data set on which we conducted our experiments. It's the WMT14 English to French data set. So there is, in machine translation, WMT runs these competitions every year. They release data sets and many teams compete. And this data set is about 700 million words, although we trained on only 30% on the training data for a technical, historical reason I won't get into. Now, the model that we used for the large experiments was not small. It had 160,000 input words and 80,000 output words. And it had 4 layers of LSTMs with 1,000 cells, which means that you've got an 8,000 dimensional state, because 1,000 LSTM cells means that you've got 2,000 dimensional states. We also use the different LSTM for the input and the output, which gives us a total of 384 million parameters. So this is how the model looks like. It's this giant thing. You've got one LSTM for the encoder, a different LSTM for the decoder. You've got a vocabulary of 160,000 words on the inputs, and then you've got 80,000 words on the output. And we have a softmax here. We just use the straight softmax of size 80,000, and then there are 1,000 dimensions that fit into it. So this is probably one of the largest naive softmaxes that ever been attempted. And yeah, so just a big model, and we just train it with stochastic gradient descent. Really straightforward, really simple. One really important point is that this model wants to work. It's no longer the case that neural network training and tuning is black magic. The amount of tuning that was required for this model was small, and all of it is described in this one slide. So the batch size, 128. The learning rate is 0.7 divided by batch size. The initial scale is uniform between minus 0.08 and plus 0.08, and we control the norm of our gradient so that it's no greater than 5. And finally, we have the learning rate every half epoch after 5 epochs. And that's it. That's all it takes to get this thing to work. And this is really important. In general, if you feel like you want to get into neural nets and you say, oh my God, this tuning is so complicated, what to do? Actually, in many cases, the tuning is not complicated. There are only 4 things you need to know in order to tune your neural network in 90% of the cases. You need to make sure that your learning rate is all right, that the initial scale of the random initialization is all right, that you clip the norm of the gradients if you use a recurrent neural network, and that you don't forget to lower your learning rate at the end. And you do these 4 things, and that's it. That's all we did here, just these 4 things. We didn't even use momentum. It's a very, very simple, bare bones approach, which was sufficient here. Another thing that we've done to train larger models faster was parallelization. And for this, in this work, we used a single 8 GPU machine, and we parallelized the model by placing each layer of the LSTM on a different GPU. And this way we were able to get a 3.5x speedup, which is not crazy, but also not too bad. And this gives us 8 times more RAM. However, I should really point out that this model can be run on a single K40, which has 12 gigs of RAM. So RAM is the main limitation. It would probably get something which would be 2 times slower because the K40 is a faster GPU than what we had. So the parallelization is quite neat. So I'll show you how it works. Each layer of the LSTM lives on a different GPU, as shown in this figure. And it just starts, each layer computes its activations independently, and it sends its activations to the next LSTM. So you got this kind of computation. It looks like that. And this is how you get the 3.5x speedup. So again, this is a bit of an engineering detail if you want to get the maximum speed, but the model itself, like I said again, it's just a deep LSTM, extremely simple, extremely uniform. Now, one nice property of this model is that we embed a sequence into a vector. We've got this nice way of embedding a variable-sized object into a single embedding. So this thing is a vector. And we can try to see what it does, and we can get pretty interesting, pretty nice-looking effects. Like, for example, we took those 6 sentences. Mary admires John, Mary is in love with John, Mary respects John. Then John admires Mary, John is in love with Mary, John respects Mary. We took those 6 sentences, we computed their vector representations, and we took 2-dimensional PCA, and we got this nice automatic clustering. So you see, it's apparent that the model has learned something non-trivial about the embedding. It has preserved the, order of the, I believe, verbs, and at the same time, it cares about the order of the people. And likewise, in this example, it's pretty interesting because here we have 3 ways of saying the same thing, and then 3 ways of saying something different. So here it's, I was given a card by her in the garden she gave me a card, she gave me a card in the garden. So in this case, in this sentence, she has given a card to I. And all these sentences say the same thing, but in different ways. And these sentences say the opposite, and it's figured out to cluster, it was smart enough to cluster them automatically. So this is a nice effect. What it means is that if you have an objective function where you want to embed sequences into, if you want to embed a sequence into a vector, you can just use a deep LSTM or even a shallow LSTM, and it will probably be very reasonable. So the results. Basically, we use the blue score to evaluate our performance, where the higher it is, the better it is. The winner of the WMT14 contest got 37.0, and an ensemble of 5 of our LSTM models got 34.8, which means that we are pretty close to the best entry of WMT14, but we are not there yet. Now, we can do a little bit of an error analysis, and we can say, well, what happens on long sequences? What happens when you look at longer sentences? Does performance deteriorate? And the answer is basically no. Even when your sentences has 35 words, it basically does just fine. And only when you go all the way to 79 words, there's a small drop in performance. The red curve is a baseline. It's kind of an untuned phrase-based system. Now, where our system suffers is on out-of-vocabulary words. When we sort the test sentences by the number of out-of-vocabulary words that they have, you see that our performance degrades very rapidly. And this is a problem. And I want to point out our follow-up work that was done primarily by Thang Long when he was an intern at Google, as well as myself, Kwok Lee, Oriel, and Wojciech Zaremba. And we used a very simple idea to address the out-of-vocabulary problem that required very little coding, which brought us all the way to 37.5 blue points. And the best entry was 37, the best of WMT14 was 37.0. So that's quite nice. The paper is available in archiving on our websites. So to conclude, we presented a general, simple, primitive approach for solving sequence-to-sequence problems. And we showed that it works on machine translation. We showed that it works well. And machine translation is a problem where you already have good solutions. So therefore, it means that if you have a sequence-to-sequence problem, or if you have something which you want to formulate as a sequence-to-sequence problem, you just apply this, and it will work. And a notable recent application of ideas like this are the recent image caption generation. So I really see this as a step towards completely solving the supervised learning problem. And so the real conclusion now is that if you have a large, big data set and you train a very large deep neural network, then success is guaranteed. Thank you very much.
Questions? We have time for a couple of questions.
Just a quick. Hello?
Hello?
Yes?
Just a quick question. So what if there is a big mismatch between the dimensions of the input sequence and the output sequence?
What do you mean by mismatch?
Like, for example, the input sequence is a musical note and the output sequence is a huge, the big analog signal.
I mean, the main limitation of this model is that it doesn't like very long sequences. As long as your sequences aren't very long, it's going to be okay.
I see.
It doesn't care. It will just find a way.
Thanks for a very nice talk. So there are many things that you might try to do with these representations after you've learned them, like try to predict properties of the input sentence, either recapitulating the input sentence or extracting anything that an NLP system might want to extract from that sentence. So I have two questions, both of which probably would be follow-up work. One is, once you've trained the system to do MT or to do autoencoding, what can you get from these representations if you freeze the weights? And the other question is, can you improve performance if you do multitask learning? So you're not just trying to do translation, but you may have supervision on some sentences. Thanks.
So, okay, the answer is that basically we haven't investigated very thoroughly we haven't investigated too carefully the properties of the representations. It's definitely true that, I mean, when it comes to unsupervised representations, the situation is always a bit tricky because the objective function doesn't really try to make very convenient representation for the other tasks. It is definitely true that multitask learning will help, especially in situations when you don't have a lot of data. If you do have a lot of data, I think multitask learning might even hurt because you just want to focus on the big data set and dedicate all the network's resources to the problem that you want to solve.
I might expect that the more different the languages, the source and target languages, the more interesting linguistic features might have to be encoded in order to transform one to the other.
It's definitely very possible. I mean, the network is, I think it would be interesting to understand exactly how they work, and it is likely that it will encode very interesting linguistic features.
Last question.
Yeah, I was curious about your grand claim that this can solve any sequence-to-sequence model. Given that you only have like 4 things to do in training, like what other sequence-to-sequence problem have you run this on?
Well, we will have a paper online in a few weeks. It's pretty cool.
What? You can't just say the task?
Sorry.
All
A
right.
few weeks, I promise.
Thanks.
Okay, let's thank Ilya again.
Okay.